Alright, so are we live? Hello. 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 Yeah. Okay. I just like to listen to myself, man. Alright, we'll take a moment. We're gonna get into sorry, I'm very I don't even know what. Excuse me, I'm in a different world right now. My mind and my brain and my freaking all the things in my mind lately. It's a little overwhelming. But today we're going to forget about all of our worries, troubles, fears, hopes, dreams, ambitions, and otherwise, and just solve a Leetcode problem. Just one. See how long it takes, how far we get. Let's give it a shot. Let's go for it. Let's go for it. Now the question is, how are we going to do here? How are we going to do? Maximum product of word lengths. Okay. Let's see. Excuse me. Given a string array of words, find the maximum value of length of word of I times the length of word of j, where the two words do not share common letters. You may assume that each word will contain only lowercase letters. If no such two words exist, return 0. Excuse me. Excuse me. So you gotta, for every pair of words that don't share common letters, take the product of their lengths, and you want to find the maximum value possible, given your set of words. There's 1,000 words, okay, and the length of the word could be 1,000. Excuse me. And each word consists of only lowercase English letters. All right. Fair enough. So, I mean, there's some ideas. I think you probably could do a round robin on every word. You literally just go through every pair with one pre-processing step, where the pre-processing step you make like a bit vector of 26 bits. Bit set. You could use a regular integer too. You don't really need a bit vector. Regular integer is 32 bits. That's plenty. Yeah. Yeah, you can just create a hash map of the strings to hash every string to an integer. The integer being like a bit mask. You just skip the pairs where the bit mask is non-zero, with the and the two bit masks, and it's non-zero. Excuse me. Probably whistling into the microphone might be kind of awkward, but I don't know. So Sometimes things that like kind of bother me, and whistling kind of gives me a moment to like sort of get my mind off of it. You know, the thing is, excuse me. Trying to think if there's a way to do this where you can find this maximum value in a way that doesn't involve going through every possible pair. If that makes sense. I want to say you could do something with a stack here, where you have maybe you could do something with a stack. Like the idea would be you want to find the maximum area, and you kind of want to do something of a round robin. But the thing is, like, you're trying to find the largest of both possible areas, right? And so in some cases, I want to say you could do something with the stack here. I hope so. But the problem is that in some cases, the word has a larger length. However, it has more letters, common letters. So what if you do like, what if we do like something a little more clever, like a dynamic programming kind of approach, something that like, if you only had these bits, or if you didn't have this letter, what would be the best possible area you can get for things without certain letters, something like that. Oh, all right. I'm gonna go sit and think about this. This is gonna take me a while to think about. This is gonna take a while. And I'm really tired. I'm like ready to fall asleep. I had a hard time falling asleep before. Just kind of becoming normal for me, which is not good. But it just feels so good to lay down. Oh, and sit and think. Yeah, I'm thinking some kind of stack-based solution, some kind of dynamic programming solution. We could do this in linear time or n log n time. Maybe some kind of sorting. Some kind of something. Excuse me. You might be able to do something clever with the with sorting too. Actually, if you sort all of the words and then sort all of those in order as well. Basically, all of the words that start with an A, you wouldn't multiply any of them against each other, and all of the words that start with a B, like maybe you could break this into. Maybe you could break the pairs into equivalence classes, and then somehow maybe you'd say like, oh, well, you know, we only need the maximum of this group and the maximum of that group. Something like that. Maximum size. I don't know. I mean, it's very, I don't know, man. I don't know. I don't have any obvious answers for this. Definitely not. So I guess one way of doing this is the round robin approach. So I guess one thing that's good is that for every pair we can, in constant time, we can decide whether or not the pair is basically zero area and that it doesn't have doesn't contribute or not, or doesn't, yeah, does or doesn't contribute. And for the pairs that are legitimate or reasonable, you know what you could do actually? Maybe you could just sort, and you would say, you know, you basically can go from right to left through the sorted list, starting from the largest, sort by the lengths. And if the two longest strings don't, what do they call that? Or how do we want to call that? If they knock each other out, they are legitimate. We'll say it's just are legitimate. We'll use that term. Or satisfy the condition. Let's just say it's legitimate. If the two longest length strings are legitimate, which you can find by sorting, and you can just take a look at the back two, then you're done, right? Then you're done. If, however, let's say those two are not legitimate, that means that either, so there's sort of two numbers, there's A and there's B, right? You could try C, and you could try C against A and B, and the larger of the two of those, whichever is legitimate, must be right. In other words, you have to lose either A or B. So drop either A or drop either B. Now the problem is you could check A against every value, B and from B down, right? So from B to the front, and you could also check every value B from B down to the front as well, and multiply all these numbers. And I guess because you would be multiplying A and C and you're multiplying B and C, since A is larger, the first one of those that's legitimate, A or B, that's the one that's got to be the answer, right? Now it could be that neither of them are legitimate all the way down, which would be awkward. And I guess there's got to be a way to do that, to just eliminate values that we know just simply will not be the way to do that, I think, is just to use an AND of the whole, all of the you AND the whole bit sets all the way across, and then obviously any values that match that, we know that there's sort of they'll basically they're all going to be legitimate. Right, those are just always illegitimate. So you can remove all those values, I think, in one shot. Do some pre-processing steps. So one pre-processing step to get from string to bit sets. Use a hash map, and then you can run through all the bit sets to get a total bit set, and then you can run through your strings to say, okay, all of these values that when you AND and you get something from the so the total bit set, if that's not zero, then that means that this one that you're looking at will match against everything else. So it's totally useless, or that particular word can be removed completely. And so you can guarantee that A and B are not words that will never reach. So they both do have some other pair that they can match with. And so if A and B don't work, then you have A or B to pick from, and then you want the next largest value for A, and then so some value C. Since A is larger than C, if A is good for A, and if it's good for C, if it's good for B and A, then A and C is what you want. However, you may find that C doesn't, basically C could match A or B, and you'd want to find the largest C that matches really either of those two. Obviously, if it matches A and B, you would pick the one that matches A. But if you pick one that ends up matching just B or just A, if it's just A, obviously again you'd pick that one. But if it just matches B, it's just legitimate with B. That has to be your best option, because no, that could be wrong, right? So you might have we'll call it X, where let's do it this way. So if A, B, and C, C is smaller than A and B, it's the next largest value. If C doesn't match, if C matches A, you pick that one. Or if C is legitimate with A, you pick that one. If C is legitimate with B and not A, then you pick that one. If it's legitimate with both, you pick A, the one with A. If it's not legitimate with either of them, then you've got to go to the next value, right? So there's 4 options. It's legitimate with A, it's legitimate with B, it's not legitimate with either of them, or it's legitimate with both of them. In each case, we know the answer, but suppose it's not legitimate with either of them, right? That's the one that's uncertain. Now, the question is, what do you do? Because it's not correct that it's the that you just go next to D and keep checking, right? Because you could have now A, B, and C that you match those against D. Obviously, if A is legitimate, you pick that. If B is legitimate and A is not, then you pick that. If C is legitimate and the other two are not, then you would pick that. But you don't really know, do you? Which one, if it's legitimate with which one's which. And you very quickly end up back in this sort of round robin kind of a thing going on, even though these are even though you've sorted first. So I guess what you probably want to do is very quickly determine whether or not this value is legitimate with the whole group. Yeah. Maybe you can do a binary search of some kind. Like, I'm wondering if you can. Even thinking of something like a segment tree. If the thing is legitimate with any of the values in a certain segment, right? And then you can basically add or remove half of the array if it is legitimate or not legitimate with that whole segment. That's interesting. That's an idea. There's an idea. So maybe you can use a segment tree to make the query, instead of its quadratic time, becomes n log n time to decide. And actually, you can do even better than that, because if you recall, segment trees are really useful when the range changes. However, you can use just a plain old what do they call it? You can use a constant time approach to figure out whether or not values in a certain range whether or not well, if you're dealing with sums, you can kind of, if you wanted to know what's the sum over a certain range, but actually in this case you want to know, is this value legitimate for any of the comparisons in some range? Are there any values in there that would be legitimate to compare against? You don't actually even need to sort anything to do that, to know that. But that is, there's at least one. But the problem with that is if it doesn't really help us that much, because we kind of need to check every section. Like maybe you would want to use basically a logarithmic search. In which case you really want to find the largest one that's legitimate with that value. I'm not sure if you really want to go through the trouble of building a segment tree. I don't think you really need to. But yeah, you can definitely. Oh, I don't know. Okay, maybe you do want to use a segment tree, because I think figuring out whether or not, like, in order to, you would use the AND operator. You would AND a whole bunch of values over a certain range, and the tricky thing with that is, excuse me. Actually, the segment tree construction for that's pretty easy. I'm just thinking the tricky thing with that is, sorry, I'm closing my eyes here. I'm kind of falling asleep. The tricky thing with that is, like I said, it's actually pretty natural for the segment tree. I don't know if you could do it easily with, like, the sum queries are kind of easy because you can do, or have a interesting property because you can do a cumulative sum, and then you can just you do some subtractions over the cumulative array, and you get something interesting. But if you do the bitwise AND, you don't really have like a, how do you do like a cumulative, how do you undo the AND operation? That's pretty much what we're trying to do, is undo the AND operation. I don't know if it's that easy to do that. Like A and B gives you C, so it's like, so do the opposite of ANDing C and A, you get B, right? Like A times B gives you C, so C divided by B gives you A, right? A times B, C divided by B. It's A and B gives you C, so A with, I don't know, negation and NAND, and negation and C gives you B. I don't I don't know if that, not only do I not think that operation exists, but you would need to do that kind of for all of the values in between these ranges, right? Like summation happens to work nicely, but I don't know if there's like a way to undo a whole section of AND operations, or just operations in general. Now, mind you, a segment tree works nicely because it's sort of already logarithmically separated into chunks, into pieces, and you're already paying that logarithmic cost. Whereas when you're doing just summations out, regular summations, you end up with you kind of need this inverting operator to kind of go backwards, something like that. Yeah, it's a little weird kind of interesting. But anyway, segment tree works, so we'll just go with that. So you can build, you can figure out. Now the thing is, I think you probably want to sort your list first, and then you want to build a segment tree to find the, basically try to find the largest value that is legitimate that you can compare against the particular, with the largest length that's legitimate that you can compare against your particular word. Yeah, I think you literally just do an n log n algorithm and call it a day. It's pretty fast. That's fast enough. It's an O of n pre-processing and storage, and n log n time complexity overall. And basically you're going to go ahead and say, let's sort our list, build a segment tree out of our list, and the segment tree is going to basically, the property we're looking for is legitimacy of the pair, right? You're going to sort of and whatever the nodes are maintained in that segment tree. You're going to and all of the words, their bit sets, and pretty much the question is going to be at that particular node, if your words bit set matches the, if you AND it with the nodes bit set, then that means that nothing in that node will be legitimate. So you return 0 for that that particular word's best pair for that node. However, if it is possible for that node, then you want to check if it's a leaf node or not. If it's not a leaf node, then you're going to go ahead and recurse to the left or recurse to the right. Now, the tricky thing is, I would say, yeah, as for the recursion, you could just return, so if that node is not legitimate, then you just return 0. You would just take the maximum of the left and the right nodes recursively. And obviously the right node, if you can't go down the right node, it'll just return 0. If you can go down the right node, you'll go down that way. I'm not sure if you even need to sort ahead of time. I was thinking you should sort because you could basically say, well, things all the way to the furthest to the right or leaning towards the right would give you like anything on the right side, those lengths are going to be naturally longer than the things on the left side, legitimate or not. So there's some benefit to sorting it first, but actually I don't think it matters because you're just always taking the maximum, and you're gonna have to check the left or the right set anyway. So now the thing that's weird though is I wonder. No, there's something wrong here. It's gotta be. You basically say, there's something wrong here because you would just end up visiting every leaf node. Like if let's say all of the words are legitimate with respect to each other, right? Then you would visit every node for every possible first word. What you do need to sort, because what you want to do is you want to say if the right side has an answer, then you could terminate early. You don't need to check the left side, and that's going to naturally give you a logarithmic time complexity, because you're going to do like a binary search. You're either going to check the left side of the tree or the right side of the tree. If there's something in the right side of the tree, you don't need to check the left side of the tree. So you just cut the number of nodes to search from in half, and you do the same thing over and over again. You check left, check right, If there's either there is something on the right side or there's not. If there's not on the right side, then you check the left side. If it's in neither the left or right, obviously you terminate very early. You just return a 0 in both cases. But I want to say something like, yeah, you should check the legitimacy first, and then return 0. And then I guess what you would do is you would recurse on the right side first, and then if it's 0, then recurse on the left side. If it's non-zero, just terminate early, return early. Yeah, that's what you want to do. That's what you want to do. So you do want to sort it. Sort it first. Sort the list of words with regard to their lengths, and then build a segment tree which has the word and basically you're going to return a length. You're looking for the largest length. You're going to use a segment tree to find the largest length that's legitimate. Largest length word that's legitimate compared to the word that you're looking at the moment. You're gonna do this for every word in the list, left to right. And yeah, you sort the words by their lengths. And also you want to do a pre-processing step where you build the bit set so checking legitimacy. You build this bit set of values, which the bit set could just be in an integer, right? Because there's 32 bits in the integer. It's plenty for 26 characters. Alphabetical characters. Lowercase alphabetical characters. Right. That works. I mean, that's fine. That'll do. That'll do, donkey. That'll do. That'll do, donkey. That'll do. Yeah. So this is kind of interesting. So we get a chance to use our segment tree again. Now, here's a really interesting thing. Can we use our segment tree in a vector as opposed to just like how we were using a segment vector before for sums, for sum queries? We don't need an update routine for our segment tree. I'm curious now, can we implement our segment tree inside of a vector? Do something very similar to what we did before. That would be super interesting. Let me think about that. Let's think about that. What would we do? We do the similar thing, right? We create all the we have the external nodes. The vector that we started with is sort of the external nodes, and they would each have they could point to the strings. It's fine to point to the strings, by the way, because the strings we can easily, in constant time from the string, we can get the the size very efficiently, right? Constant time, and also we can use our hash map of the string to get the associated bit mask that we pre-processed. So that's fine. That's great, actually. So then we have just a doubling of the size of the nodes. Then each parent again would just be tricky thing there though is we actually want the bit masks. So that's a little bit tricky. We want the length of the strings and the bit masks, and we don't really need the strings themselves. We just need the lengths of the strings. We don't really, the bit mask and the length should be fine. Yeah, because we want that pre-processed basically in the So do we want? Can we do pairs? We can. That works. You could do that. You could do pairs of lengths and bit masks. That's kind of interesting. Just trying to think about that. Like, what do you? Yeah, I think that works. We could just use a -1 for the internal nodes, and the external nodes have an actual integer associated with them for the bit masks. And then you have the set of internal nodes, you have the external, where the external nodes begin, the internal nodes just a copy, right? And you can do the same kind of routine where you have where you set up the pair for each parent. It's basically the two children. You take you AND the bit masks to get the parent's bit mask, and you don't actually. You just have a -1 for the internal nodes for the size of the string, just to denote something kind of like should be ignored, I guess. And that would build the vector, build the tree, and then querying. We don't even need to update, so I don't have to think about that. But querying would be, what do? You left side, right side, you would, where would you even, the queries previously would be, there's some queries, but we're not looking for sums, we're actually looking for maximum. I think we should use the recursive approach, right? Going down the tree, through the vector, down the vector. I think it would be weird to try to go up from the bottom of the vector upwards towards the top. It doesn't really make a lot of sense because we don't actually know where the whole point is we don't know where in the bottom we're going. So we can't really do that bottom up. We have to do it top down. And yeah, you can use you don't even need to use what do they call that? You don't even need to, so you really just have a key that you would use. I don't know if this is really maybe it's just a binary search. Maybe you don't even need a segment tree. I don't know, the more I'm thinking about it, it's like, wait a minute, is this even a segment tree anymore? That we're just a binary tree? I don't know. Yeah, well, let's say it's a segment tree. Let's go with that. We'll just keep going with the segment tree. So the query would just start from the top, and it would go to the bottom. It would process, get some leaf node, and then just return. Yeah, as I said, it would recursively search. So yeah, you would use the vector in place of the binary tree, and obviously just multiply by 2, and the right node would be ORed with a 1, or yeah, multiply by 2 and or with a 1 to get the right node, and OR with 0 to get the left node. Just multiply by 2 to get the left node, multiply by 2, and then OR with 1 to get the right node. And pretty much you process the right node first recursively. That's really all you have to do, is just recursively process the right node and terminate early, and that gives you a logarithmic running time. Excuse me. Yeah, pretty interesting. So, and yeah, you do that for every. You have some bit set that you compare all these other bit sets to for each word, and then you also have the length for that word. And then after you process your segment tree, you query your segment tree with this other bit set as the key. You just multiply the returned value by your original string's length. That gives you some number, and then you do that for every. You basically stick that into a maximum value, and then do that for every possibility, every word. Kind of neat. Yeah, I guess a pair is fine. A pair for the data and the vector. We're gonna give this a shot. We're gonna try to use this segment tree, use our own little segment tree implementation in a vector, and see if. Also, I stood up way too quick. Oh, that was way too fast. Oh, give myself a moment so I don't fall over. Get a nice blood rush going. Yeah. All right. See if we can do this in n log n time. Let's see how this works. Let's give it a shot. I don't know how it's gonna go, but we'll try it. See what happens. Try it and see what happens. Excuse me. Wow. Yeah. Let's see. Just give me one moment. I want to just notice something here. I think I got an idea. Got an idea. Good evening again. Hey, how's it going, Simon Steinen? If you sort it by length, once you've found a match, you could potentially start removing parts of the tree on the right side. As the first word gets shorter, the second word needs to get longer to yield an equal or greater multiple. Would it make more sense to create a bit mask length pair? The length is equal to sight or smaller than the pointer, saves an indirection, and the original data is no longer required. Yeah, I think that's a good idea. Welcome, Simon. Yeah, I agree with you also. Sorting by the length. There's definitely other ways to do this, approach this problem. I'm gonna try it with a segment tree first and see if I can get an answer, if I can do it. And then I bet you there's something to do with sorting by length and then removing pieces possibly or something. I don't know. I haven't really thought that far ahead to figure out what you could do. However, I agree with you. I think a segment tree and then exactly a bit mask length pair was exactly what I was thinking. I agree. Let's see what we end up with here. Let's see what we get. Also, yeah, welcome. Glad to see you again. I appreciate you coming by and saying hello. I appreciate it a lot. We want a. We don't even need we don't even need an ordered set anymore, because we can do so. Let's do this. Let's say vector, a pair. We'll do the bit mask is the int, and the length is an int as well. And we'll say bit mask pair, length pair. And now we say this is going to be 2 times the words dot size. And it's going to be, let's just do that. And we'll say, the bit mask itself, have a routine, find mask, we'll call, or just get mask, or just mask, let's just call it mask. And it's going to be a lambda routine that we have here. We're going to have const standard string s, and we're going to say for C and S, we're going to have int ret equals 0, and we're going to say ret or C. So here we go. We go C minus A is going to give you some number, and we're going to take 1, and we're going to bit shift the 1 that many positions over, and return ret. So that gives us our bit masks, right? And then we want to say, yes, we're going to have these pairs. We're not going to say, yeah, we're going to have excuse me, we have default pairs. So int external is going to be words.size. We're going to, we want to sort by, we can actually do something kind of interesting. So we can, let's try this. So we can, I want to sort, well, okay, we can do this. We can do this. So for int I equals external, I is less than bitmask length pair dot size increment I. We want to set bitmask length pair of I equal to standard make pair of two things. We want the bit mask and then the length. So the second one value will be the length. The bit mask is going to be words of I. I don't know. Well, we want to kind of make like a copy, but we don't want to just copy. We want to get the mask of the word, mask, and then length. And now the thing is, it's not words of I. It's going to be, or size. But it's not I. It's going to be I minus external, or yeah, basically 0. We can do this too. Use move semantics here. Hopefully that works properly. I don't think we actually need to put that there, but we're going to. So I minus external and yeah, I minus external. So it goes 0 to this length, which may seem a little confusing at first. But this difference between external here and this size is exactly word size, so this should be fine. We want to put those in the back, and now we're going to go the other way. External minus 1, I greater than or equal to 0, minus I, and we actually don't need to go to 0. 0, we don't actually need to go to 0. We can go greater than 0, should be fine. And now we're going to say bit mask length, or we'll just say tree. We'll do tree. I think tree is easier to work with. Tree bit mask length pair. Tree of I is going to be, now this is going to be I bit shifted to the right 1, no, bit shifted to the left 1, multiplies by, yeah, tree of this child and the other child, right? These are the two children to consider, and we're actually going to say auto P1 or L, let's say L, reference L is this guy, and reference R is this guy. So left node, right node. And now we want to say this is going to be standard make pair of all of these are our internal nodes. The length is going to be -1, and the bit mask is going to be the AND between the two bit masks, which is, so new mask is going to be the left mask, which is, we said, first, and the right mask. I have a new mask. There we go. Okay. So now we build our segment tree. Okay. Oh, we want to, before we even do that, sort by length before proceeding. So we want to say standard sort of its tree. Tree. Now it's not tree.begin. It's tree.begin plus external to tree.end. That's what we want to sort. And we want to use this custom comparator function, which we'll set up in a second. I'll explain that. And we want the beginning plus external sorted with to the end, right? And you're going to sort these based off of const pair of ints A, and the same thing B. You want to return the lengths, right? Which we said the lengths are going to be the second one. So A.second less than B.second. There we go. All right. So that should sort. We're going to process the words, put them into this vector, sort the right side of the vector, and then after doing that, then we're going to build the parents to the vector. Build internal nodes. Right. External nodes. Now we want the query routine, which is going to be query a bit mask. We'll call it bmask. So now the query is, we're going to find basically the largest length for a particular bmask, which is going to be given a particular bit mask. Find the largest length associated with any bit mask in the segment tree. And that would be legitimate. When combined with B. Yeah. Given a particular bitmask B, find the largest length associated with any bitmask in the segment tree that would be legitimate when combined with B. That's really confusing, but hopefully that makes sense. And you're going to do a recursive approach. And so you say base case if, and you really have an int position, we'll say. If position is less than 0 or position is greater than the tree dot size, or yeah, just do that. Return 0. Base cases, let's say, or sanity checks. Sanity check. Base cases. So you've got this bit mask, and you have bit mask in the tree. So for this position, we have the tree position. So there's two, oh, it's so distracting. There's two cases, right? If we're in an external node, we return the length. If we're, so we want to know the position. So the base cases are if position is greater than or equal to external, then return tree of position. If tree position of, we want to get the bit mask, int mask is going to be tree of position. We can even just do this. That's probably better. Can you do this? I think you can even just do length mask, or length mask, right? Is it length mask or mask length? Is it mask length? Right? So you can do mask length. If the position is greater than or equal to external, then you simply return the length. If otherwise, right? If the mask and the B mask are greater than 0, right? Which you don't really have to put that, but you can just put that there. Then return 0. And finally, recurse. The recursion is going to be int a equals query of the right side, first the right side to terminate early, which is going to be same B mask, same F. I feel like I need to sneeze. Excuse me. I don't feel like I need to sneeze. I did need to sneeze. Oh, my head, my whole face went into that one. Achoo. Achoo. Whew. Whew. Okay. Now, so we're looking at the right child, which is going to be position, bit shift to the left, 1. See, if you ever shift all the bits to the left, you multiply by 2, right? So that's going to be position, bit shift to the left, 2, mask F, and then we say if A is greater than 0, then we're going to return A. Otherwise, if B is position left 1 or 1, B mask F, return standard maximum of A and B. Right? So we get the right side. It should be 0, and then we would end up just returning B. I don't think if you don't get the right side, well, yeah, because the right side and the left side could both be 0. In which case, I guess returning the maximum is the simplest thing to do. Terminate early on the right side, order to ensure logarithmic time complexity. Now we have our query, and we're going to loop over every word. So we say for auto w words, and excuse me, we're at 0 for each word. We're going to query starting from position 1, should be just 1, which is really the head. Query position 1 with query as the recursive function itself, and we want to use the mask, which is mask of w, and we're going to get some length, and we're going to say ret equals standard maximum of ret and the size of w times this query. Alright, does this compile? First question. Warning, has lower precedence, will be evaluated first. Alright, I'm glad that we checked that. I made that mistake before also with the precedence, issues with precedence. No matching call to max. Really? Deduce conflicting first unsigned long. No kidding. Oh yeah, because this is a, okay, interesting. Gotta be careful. Oh. Well. Nifty. Bless you. Thank you. Thank you. It looks like we compile. We get the wrong answer, but we did something interesting. Pretty interesting that it compiles. Only really made 2 errors. Oh, I know why. The rat's not the right side. That's the left side. That might have something to do with it. No, didn't matter. What happened? What happened? What did we do wrong? Is our logic wrong? I don't think so. What could have gone wrong here? Well, what's the right answer for that? Well, 16, right? What are we supposed to get? We're supposed to get... We can do this by hand, right? This round robin. Can we not? This is 1, 2, 3, 4, 3, 3, 3, 4, 3, 3, 3, 4, 1, 2, 3, 4, 5, 1, 2, no, 6. Right? 1, 2, 3, 4, 3, 3, 3, 4, 4, 6. Okay. All right. So 4 times what for the first one, right? So we can do not itself. B doesn't work with B. 3 gives us 12. Works for 3. Doesn't work for this guy. Doesn't work. Works for 4 by 4. Gives us 16. And 6 doesn't work for 6. All right. So we got 16 is the best so far. 3 doesn't work for this. We really don't have to go look at the back ones, right? We can just go right. 3 by 3 is 9, which is we don't care about. Don't do that one. 3 by 4, which is 12, which is not better than 16. And then 3 by 1, 2, 3, 4, 5, 6, 18, right? 3 by 6 gives us 18. Now that one doesn't work though. That one's no bueno. We got 18 though. The question is, are my masks correct? see, that's a good question. Now, did I do this right? The masks on the left, the size on the right. Mask on the left, size on the right. This is the left node, left subtree. This is the right subtree. Now, is it possible? Oh, I did this wrong. Of course. Duh. Yeah, that order of operation matters a lot, right? Because you have to check the mask before you return the length, right? Of course. I like the warnings there. I had that precedence warning yesterday as well. Yeah. That's important. Probably have a type mismatch there, so I kind of deduce the template parameter. Right, something. I think it basically looked at this one is an unsigned long, and then this one, right, is sort of an auto. Doesn't really tell you exactly what it's supposed to be. It's an integer, but we could do that too. That should work. So now the question is, oh, well, okay, it's better than 18 because, 18 was wrong, but 12 is still wrong too. Excuse me. Oops. I think it's clear that 18, wait, they said 18 is the answer, right? We can't, oh no, I'm sorry. Not 18. 18 doesn't exist for this. That's 3 by 6. And then 3 by these others, the best you can do, I think, is still 12. Wait a second. Yeah, foo doesn't work either here. So you get 9 and 12, and then bar doesn't work for 3 by 6. That's still 12. And then 4 by 6 is illegitimate. So 16 is the best. Okay. So I guess my first question is, what does the tree look like when we sort it? Let's just make sure we sorted this correctly. Right? Debug for int I equals 0, I is less than tree of end, or tree size. Tree of I of the second, we said, is what the length is. I just want to see what happens here. What do we got? Okay. 3, 3, 3, 3, 3, 3, 4, 4, 6. Yeah, alright. And these different bit masks, right? They should all have different bit masks. Not really sure how to print the bit masks. So we have 6 of these. 1, 2, 3, 4, 5, 6. And we should end up with 5, right? Only 5 of these nodes really need to be oh, oops, not that one. After we build the internal nodes, let's make sure we have. Yeah, we don't care about these lengths. If we have an AND, we return 0. Oh, excuse me. No. Wait a second. No. This is. Hold on. I had that. Wait a minute. Well, that is really confusing. Hold on a second here. What are we doing? This was right the first time. If your position is the external nodes, you're done. You don't care if you match the bit mask or not. Oh, but you do. Okay. I think I got it. All right. No. I'm doing this all wrong. Yeah. All right. Let's do this. Say bool legitimate. right? We actually have it has to be equal to 0 for it to be legitimate. If this is true, then so really, if it's legitimate, if it's not legitimate, we don't care. If you're legitimate, then you return. Then you have this if statement. If position is greater than or equal to external, return length. Oh, this is so confusing. There's really only two base cases. It's if you're not legitimate, return 0. If you are legitimate and your position is greater than or equal to external, you just return the length. The logic is kind of confusing for this, huh? But how come? Did we have this right the first time? If you're legitimate and your position is greater than or equal to external, you return the length. If it's not greater than or equal to the external, that means it's one of these guys, then you got to consider the children. So I don't know, if we query, like, we should actually get 16 for this guy, yeah, this first query, ABCW. If we do that, what's ABCW look like? Let's just print that right now. Let's do 32. Let's say 1 bit shift to left I, and with test, that's a 0 or 1. Let's just say greater than 0, right? What does that give us? Can we do this? Okay. Alrighty. ABCW. Oh, that's pretty interesting. Look at that. Alright, that's our bit mask. Why? Yeah, okay, I guess. Doesn't really matter. I was just thinking we have all these extra bits on the right side, but we'll just leave it as it is. So we have this bit mask, ABCW. When we query, we say, let's mask of this W, query, size is 4. This one should give us 16. We take a look at the start, at the beginning, and we say, where is that, -1? Yeah, -1 here. That bit mask, I guess what do we want? I don't know. I don't know what to do exactly. What we would expect is the left and the right, and this spot in particular, we would say it's legitimate, right? However, it doesn't fall into this category, so we would say the right side A and the left side B, and we'd have the same mask. The right side would be times 2, so this is 0, 1 times 2 is 0, 1, 2, and a 1, 3. And the other one is, so the left is 2 and the right is 3. And we go to the right first. and then we multiply by 2 again, so it's 0, 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7. Yeah, because we add one to the right side, so let's go to this right node, which somehow doesn't seem right to me. That's not the node I'm thinking of. 0, 1 times 2, 0, 1, 2, which really becomes the right side, right node of that. And then the right node for that guy is, as 3, would be really 6, 6, 7. Am I crazy here? Am I going crazy here? That looks like the left side. That doesn't look like what I'm looking for. What am I missing here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 would bring us, the parent would be 5, right? And 10 would be 5. And the parent for 5 would be 2. Right? 0, 1, 2. So how does that work? How do we end up with... That's on the left side of the tree. Am I crazy? Am I going nuts? Am I just a crazy person? Well, how would these nodes, which are on the right side, how would they end up on the left? Huh? How did they end up on the left subtree? What is going on there? I think maybe... Also makes me question, how did I do this before, where I got it correct, where I was building a segment tree? It looks like I'm missing something important here. These definitely should be sorted at the end, but somehow the parent nodes are not what I'm expecting them to be. Where is the... Building the internal nodes, yeah. So... yeah, so definitely the left and right nodes, but I'm not expecting the left and right nodes to be where they are. 3, 3, 3, 4, 4, 6. Where would you expect these to be? What are these? 12, 6 nodes. 1, 2, 3, 4, 5, 6. And there's a 0 node up here, right? 0. And it's really 11, right? 6 times 2, 11. 10, 9, 8, 7, 6. This has a parent. 5. 4. 3, as expected. And then these have parents. 2. Oops. And 1 and 3, when you divide by 2, gives you parent, node 1. And that's the right node of 1, which is the really interesting part. These are actually attached to the left node of, I guess it would be 1. That's the weirdest thing. Generate all the internal nodes necessary, and then on the same depth start filling up the external nodes. This would be correct if every depth level contained either internal or external nodes. You generate all the internal nodes necessary, and then on the same depth, start filling up with the external nodes. This would be correct if every depth level contained either internal or external nodes. Oh, you're saying if every level was only internal or external. That's pretty interesting. Although what's weird about this is this segment tree style worked correctly for the range query question that we were looking at before. You didn't need to modify it. I think the issue is that it doesn't necessarily matter for the range queries which side the left and right subtrees were, because the sums didn't really care how it's commutative. The summations are commutative. So I guess we got away with it. It didn't matter, which is so weird. Because I did notice this too before, and I was like, is this wrong? Like, it's not what I was expecting. So there's a subtle nuance here that's pretty important, that your right subtree actually could end up on the left node. Now, what I'm wondering is if it's really an issue of not using the 0 node here, because if we use the 0 node and made everything here 2 to the n minus, 2 to the 2 times x minus 1 nodes, or it would be 2 raised to the n. I don't even know how to basically utilize this guy. What would happen is, if we did the other way, we did 10, 9, 8, 7, 6, 5. Wondering now, you do this, and now you get each of these nodes. Excuse me. 5, 4, 3, and then now you have 2. This still goes to 1, but now these both go to 0. No, you still get the same deal. 0, 1, 2, 3, 4, 5, 6. Oh, I'm sorry. Whoa. 6. Actually, I don't know. Hold on a second. I'm confused now. Man, I just confused myself. Let's do it this way. 0, 1, 2, 3. Let's do it this way. 4, 5, 6, 7, 8, 9, 10. So the right side it should look like this. Something like this. Now that doesn't seem right either. That doesn't seem right either. This is definitely not correct. Definitely not correct. Alternatively, you could rotate the range of external nodes. There are 2 external nodes on the 3rd level, so if you rotate the external range by 2 to the right, they would be in the correct order. I gotta think about what you're saying there. Definitely confused by that. In this case, its left node is just 1. The right node is add 2. And then the left node from there is add 2, add 3, add 3, add 4. And This doesn't seem right at all. This doesn't seem right at all. Oh my... genitals. Ouch. What is going on here? This is, how did this work before with the segment tree? That's so weird. How did I do, somehow this worked before. Somehow this worked before. It doesn't make sense now. I feel like I've been duped. I've been duped. Excuse me. Whew. I almost want to say, like, if you took every, you multiply by 2, you could also 2x and 2x plus 1. If you do 0, you get 0 and 1. That doesn't work very well, but if you use 1, you get 2 and 3. And then if you do 2, you get 4 and 5. 3 gives you 6 and 7. 4 gives you 8 and 9. 5 gives you 10 and 11. It works so nicely for, if you start with 1. However, it would seem that the right side, that is the right side. Multiply by 2 and add 1, you get the right side. So how come going backwards doesn't seem to work? Oh, I guess. Oh, I think I understand. It's because, yeah, look at these nodes, right? These 6 nodes are not going to end up on the same segment of the tree. I think that makes sense. Yeah, I have to read what you're saying because it probably sheds some light on the questions I'm asking here. I think I've become so much more aware, by the way, of like how many times I say because I've been watching commentators talking about the press secretary for the White House, Jen Psaki, and how she says something like 400 times, 350 times in 30 minutes. It says on an average of 5.3 one time every 5, on an average of once every 5.3 seconds. That's a lot. That's a lot. So now I'm trying to pay attention how many times I say Yeah, see, these are on different trees. That's the problem. These are supposed to be on the right subtree, and these are supposed to be on the left subtree. But somehow, we ended up with these on the left subtree and these on the right subtree. Look at that. Look at that. One solution, I suppose, would be to actually round this up to a power of 2. So that way 6 and 7 are contained here. So, or do it this way, where, yeah, these 6, so you can still do the same structure, you just have a little bit of extra space that's being used. Oh, no, but yeah, or, yeah. Yeah, yes, round up. So that way you would use these 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And what you would do is you would say something like, now you kind of run into some trouble here, don't you? You make these more or less, you could do length 0, I think, in the bit, or the bit mask of full bit mask, so it always returns 0. Length -1, full bit mask. Basically padding. Yeah, pad these extra values. So what would this look like then? This would be, you gotta round up to the nearest power of 2 to contain your elements of n. So what does that look like? And take log base 2 and raise it to the roof of log base 2, and then raise that to the power of 2. And that's the number, that's what power you need to fit these values. And then you can do exactly the same algorithm, you just need to pad from the right side or the left side. You actually don't necessarily need to pad the left side, you can pad the right side too, it doesn't matter. You just need to fit them all on the same level. So that way you don't have this swapping in terms of position. I agree with, I think I understand what you're saying. Basically, it didn't matter that these were in the different positions. There was no order that we needed to maintain when we were dealing with the segment tree earlier. We were dealing with range sums. It didn't make a difference what order we added them together. I believe. I think that's why it worked before. Ooh. Alternatively, you could rotate the range of external nodes. There are 2 external nodes on the 3rd level, so if you rotate the external range by 2 to the right, they would be in the correct order. I think so. I think what you're saying makes sense. I think so. I'm not entirely sure what that means. Problem here is that you can descend to the right. You will strictly do that, assuming you'll find the better the result there. Maybe that wasn't the case in the previous problem. That is different too. The difference, I think, though, is actually that this relies on, yeah, it's related. This relies on the strict ordering of the or the strict ordering of the values, the leaves. Whereas the previous segment tree is just a sum query, a range query. The order doesn't matter as long as you get all the values in there. Instead, the algorithm looks only at the bottommost nodes, the leaves from left to right without regard for the depth. A rotation will fix that. Yeah, like I said, I'm not entirely sure how I would rotate, nor what that necessarily means. I don't think I really understand. Like, what would a rotation be exactly? 6 number of external nodes is 2 away from the next integer equal power of 2, so rotation by 2 is required. If there were 7, an additional internal node would exist, so only rotation 1 would be required. Yeah, I'm still not totally following you, but I guess maybe what you're calling rotation is the same thing what I'm calling, which is basically use a complete tree and just fill it with dummy nodes, so that way you have the correct tree structure. Yeah, let's do that. Let's give that a shot. Pretty interesting. So we need external. We're going to start with that's external word size. We actually want int bottom size. We'll call it. We'll do that. We'll say this is n. The bottom size is going to be standard log of 2 of n, which is a double standard ceiling, which then you raise that to a power of 2, and then you make that an integer. I don't like doing this. This is the largest power of 2. This is the largest power of 2 that's smallest power of 2 that's greater than or equal to. And alternatively, now mind you, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's what we need. Now mind you, we also require. So another way to do this, if n there's another way to do this, which is basically you would bit shift it to the left, or no, you would find the furthest bit to the left, the most significant bit. Yeah, grab the most significant bit, and then if that's equal to your value, you're done. Otherwise, multiply it by 2. Bit shift one more time. So some bit manipulation. I can find the least significant bit efficiently, but I don't know if I can find the most significant bit efficiently. I guess if you reverse the bits, find the least significant bit, and then yeah, I like doing that more than this algorithm because of I don't like floating point errors. I don't think I'll get floating point errors with 32 bit ceiling. I assume it's not available in Leetcode though. Fail to recognize pop count these days. Yeah, interesting population count. There's a link in there between the problem and instead the algorithm. Probably got moderated. Oh, oops. Yeah, I probably got automatically remove the link. Maps down to intrinsic though, so you could just write a loop to find the most significant bit and trust the compiler to optimize it. Yeah, that's a right pop count. Yeah, I'm aware of pop count. Or there's another routine that gives you pop count gives you the number of bits, but you're looking for we could just do it this way. This is a simple way to new n. You do int I. Or no, I should stop using the word I. Should stop saying I gotta stop saying I is less than 32. You say new n equals the maximum of, we do it this way, better yet, we do if 1 bit shifted by I and 1 bit shifted by I and n. If that's true, then you're going to update this new n equal to 1 bit shifted by I. You could even optimize it a little bit more too. Right. Now you say if n is greater than new n, then new n equals bit shift to the right 1. Or if they're not equal. Now, small problem with this, you might notice. Suppose you had something in the range from, something in the range from 2 raised to the, well, we don't have that many nodes actually, we don't have to worry about that. What I was thinking though was, how about you had nodes in the a number of nodes in the range that exceeded the 32 bits. So you had something between 2 to the 31st. Wait, how many bits do you have? Oh no. Oh no. 31. Well, 31 bits is really all you can set for integers, right? Positive integers. Start running into some issues. I think you don't. I don't know. You'd start getting. Yeah, you wouldn't be able to interpret this anymore. Actually, if you did more than 31, right? So really, you'd have to do 31. Yeah, but if you had really large values for n, you'd start running into problems because you wouldn't be able to just bit shift to the left. By the way, it's bit shift to the left, not to the right. So this will give you the largest power of 2 as well. So this also will work. So this new n, and now we say, yeah, I mean, you could do that. I think, what happens now if we do this? What do we get if we do this now? Overflowed. Let's think about this some more here. So n is word size. We get this new n, which is the largest power of the smallest power of 2 that's greater than or equal to this n. Now we want, that's how many nodes we want on the the remaining nodes in the back side, I suppose. We're going to, now this is kind of interesting. We need to go from external. You know what we can do? We can do something like this. This is a little easier to think about. I kind of prefer doing it this way. Just do basically two iterators, 2 pointers, so it's easier to think about because it just gets confusing if you try to figure out the math from there. It just gets way too confusing. And I would say you put them tree of I. Yeah, it doesn't matter. The last pairs you want. Let's even do. Let's do it this way. Fill the remaining nodes with empty pairs for, we'll basically do this, finish this off here. Oops. J is less than tree size, increment J, and do this. Make a pair, and we're going to do a full mask, which is int full mask, which is effectively int max, I believe, right? More or less. Just thinking, yeah, I think so. Full mask. We'll just do full mask. And we'll do -1. Can you do this? I like to stop. I like to keep things kind of on the same line if I can, keep it concise. I would split into multiple lines though in the case that it's just like a mouthful. You know, it's like it's hard to understand what you're looking at. I gotta read what you're. Oh, thanks to stream. Have an excellent day. Oh, you're heading off. I'm sorry. Past midnight again. I'll go to bed early tonight. Okay, yeah. Take care. It's good seeing you, Simon. I'll talk to you soon. Thanks for coming by and saying hi. I appreciate it. I appreciate chatting with you. Actually, I gotta read what you said. You got quite a few things here. I kind of want to, I guess, finish what I was doing and then I'll read the chat. Thank you for coming by, man. I appreciate it. What happens here? Wrong answer. 0. Nice. Okay. So somehow we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Or yeah, 16 nodes, right? That's a full binary tree. 0 to 15, right? There should be a 0 at the top. And that's great. That's what we want. However, somehow we lost all the lengths. Somehow we lost all the lengths. I don't know what happened there. Or maybe I'm crazy. Maybe I'm crazy. I'm missing something here. Standard fill for the remainder. Oh, maybe I should do that. Yeah, I'll add those things. I'll do that. Debug 1, debug 2. 1, 2, 3, 4, 5, 6. Oh, that's... Oh, we didn't build the internal nodes yet. Oh. Look at that. Huh. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now somehow we got 10 of these. I don't know what happened there. This should be... really should only be 8 down there. So what the heck happened? Make pair of I external is a new n, which should be 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 should be words of J. 0. Full mask, J. Oh, that's probably why. Yeah, of course. Duh. It's actually external plus J. Really, it would be words.size. That's, I think, what it's supposed to be. I think it's supposed to be something like this. I think I confused myself with how much filler there should be, with what the filler should be. Oh, now we're correct. Okay, there you go. Yeah. Now it's interesting. Okay. What's kind of peculiar is I would expect J on the right side to be the filler. It looks like it's on the left side though. Now why is that? Oh, that makes sense. No, it doesn't make sense. Why is that? Excuse me. What? External 0, 1, 2, 3, 4, 5, 6, 7, 8. Now that's really weird. Oh, because we sorted at the end there. That's why. Yeah. Don't sort it. Well, actually. That's why. There you go. Yeah, see? Now when you sort it, it makes sense. Okay. Pretty interesting. Pretty interesting. Well, it's a good thing I used the -1 over there. Yeah, that's kind of neat. Anyway, correct answer now. Now we have the right answer. Okay. no kidding. No kidding. This question, man. All these debug codes. All this debuggering. All this debuggering. You don't need that anymore, do you? Oh no. Wait, what? Oh. Okay. Sweet. Let me read what you have to say there, Simon. Let me just take some more test cases. Alright, so we needed to do some finagling to make sure our tree looked right. Our vector and our tree had made sense. What if we do an empty one? Could be 0 words. Yep. Okay. Could be a bunch of gibberish. I mean, how much gibberish can you have, really? How do we do? Let's find out. Oh, did make a mistake. Got it. Perfect. Sweet. Not bad. Not too shabby. Pretty good. 70%, 53%. Alright. That took me forever, though. That took a while. It took me something like 2.5 hours. 2 hours. Okay. Wow. Brother. We probably could do it faster than that too. Probably don't need a segment tree, something like that. Probably could do this even faster. I want to say you probably could just sort the string on lengths and then no, well the segment tree helps with regard to the legitimacy, right? That was the whole problem with the bit masks and whether or not these words are legitimate or not. Oh, we didn't do a pre-processing step. I forgot to do that. So we don't have to call the mask function so many times. Yeah, that's my mistake. That's actually kind of a considerable mistake. I mean, it's not that big of a deal, but it kind of matters. It kind of matters. Well, let me think. Does it matter that much? We build this once. Yeah, I mean, it saves calling this a few times. Well, we'll call it once instead of calling it multiple times. I don't actually know. If this is faster or not. I don't know. I don't know if this is better or not. Anywhere you see mask, bit masks. Doesn't do much more for memory, but I think it'll make it a little bit faster, potentially. Nope. Just uses more memory. Same speed. Alright, never mind then. Yeah, we don't really call that function enough for it to really matter. And it's not really necessary. Oh, a little faster this time. Kind of randomly. So, okay. There were 7 internal external nodes. Internal node link in there between. So the problem in, oh right, gotcha. Probably got moderated. Bit ceiling in bit. Assume it's not available in Leetcode. Oh, interesting. Bit ceiling. Yeah, that's kind of failed to recognize pop count these days. Yeah, interesting. There's, right, maps down to an intrinsic though, so you could just write a loop to find the most significant bit, trust the compiler, optimize it. Yeah, there's a way that's like optimal, I think, to do that, do this operation that I'm doing here. However, for now, we'll leave it as it is. For I, if I is less than, if for I, dot dot dot, I greater than or equal to n equals its value break. Anyway, past minute, I go to bed early. Yeah, I mean, I just do the whole thing if, basically, if it's greater than or equal to n. You can do it that way too. T is great. Yeah. That's actually probably better. Let's do it that way. I like that. I like that routine better. That's a better one. It really doesn't matter that much, but I think it's cleaner, easier to understand. Thank you for that. I like that better. Past midnight again, I'll go to bed early tonight. Thanks for the stream, excellent day. 2 variable for loop could be replaced with standard transform kit, couldn't it? I think so, and standard fill for the remainder. Yeah, I agree with you. I probably should. Transform. Yeah, there's definitely something in the STL that I could have used here that I probably should have used. Let's see. Unary operator. Yeah, let's use a input, output, unary operator, output first. Let's give that a shot. So it's going to be something like this. The input operator, so standard transform, input is words.begin, ending is words.end, and the output is going to be tree.begin plus external, and the lambda is let's just, I don't know, lambda 1. Let's call it lambda, or just modify const standard string s turn standard make pair. And I want to even do this if I can. I don't know if I can. I think copy elision should work properly, but okay. Well, yeah, all right. Mask of s and s.size. And so use modify here. True. Do something like this. Compiler fill. What does that give us? The transform is exactly what we were looking for. We didn't, excuse me, mistake there. Iota fill, isn't there a fill? And I'll be alright. Where is fill? Is there a fill? Algorithm. For iterator in, yeah, okay, sure. Begin, end, true. Tree.begin plus external plus words dot size to tree.end. Make pair full mask. Now does that work? What happens if we do this? Still works. Makes use of the STL. Awesome. That is so much cleaner. Oh, it's so much nicer. Yeah, I definitely like code like that, where you can just use a few subroutines, make things super clean, make things very clean. You can actually use an accumulator function on this, I think. Make this lambda a certain way, and use an accumulator for the ret value, which I want to use that next. Do that next. Yeah, I like kind of going through and cleaning up code with some STL algorithms. However, I really don't use them very much. Yeah, I don't use them very much. Let's give you a const expression too. And I'll be alright. Wow, that's a lot faster, huh? And I'll be alright. This really could just be int max, huh? Kind of like the full mask though. So there are some things here. The filling I think is good. So I wonder if you did this, what this would do. I don't think this makes sense actually. Does it still make sense? Yeah, it does. You really don't need that. Yeah, a lot of the copy elision, or the what you would call move semantics, a lot of it is kind of built in already to a lot of the copy constructors. I think the move semantics is built into a lot of the copy constructors. So yeah, if I was a little more on my toes, on my feet, I could have written transform with the modify routine. And I could have written the fill with the fill routine as shown. And finally, I think accumulate I can do here. Let me just, there's a routine here. We have this binary operator. Initial value operator, kernel accumulation, and the value of the kernel would be, yeah, so we're going to do, I'm going to try to use accumulate here as well. op or bin op or accumulate like that. We have two up. We have an int, const, int, reference a. Is that const? Yeah. And it's actually type 1 and type 2 not need to have const. Okay. Const standard string s, and we're going to return standard max of a, and this of using query one mask w query return a of this, whether it's w is really s, and we can return accumulate of w words dot begin, words dot rods dot end, and initial value 0, and accumulate. And we can try that. It's another way to do this. Modified lambda doesn't need to capture. So I think I agree with you. It does. Needs the mask. Needs to at least capture the mask. Standard transform returns the iterator that standard fill is supposed to start from. Oh, no kidding. Oh, I agree. Oh, you're right. Ah, look at that. There you go. Wow. Well, you can actually even do better than that. I like to do this. This kind of a thing. Oh, look at that. That's a little awkward though. Well, you could just do this. Right? Really want to get fancy. Not fancy, but just change things up a bit. Oh, it's not W size, it's S size. There we go, look at that. Does that compile? Or is that still correct? Hey, look at that. Check me out. And in standard transfer, is the mask used elsewhere? If not, it could become part of modify. Oh, look at that. It's used in one spot. Only one other spot. Although you could just only capture the mask. Look at this. Look at this. Boom, 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 boom. I thought you said you were going to bed. What happened? Yeah, look at that. You can do fill, transform, and P. Oh, yeah. And obviously, this could just be put right here. You don't even need this anymore. Yeah, the reason why I have all these variables is that I like a multi-line calls. You know, I kind of want to I want it to be legible, I guess. Something like that. This is legible enough though. This, you can see what's going on. So you transform from words begin, words end into tree begin external. You call modify on all of these words. And you get an iterator, and you're going to fill from the end of that to the end of the tree. And then, oh, that's awesome. Yeah, that's a lot cleaner. And then what you're going to fill it at the end of the tree with is these pairs, these full mask pairs. Sweet. You don't need this output anymore either. Forgot about that. I think that gets optimized out anyway. Let me see. Wondering if there's a way to run this routine as well. Nah, I'll just leave it. No, we do use the mask elsewhere. We use it here. We also use it down here. So, right, but you could use your accumulator function. This isn't really that much better than writing the loop, though. I think that tends to be why I don't really use the STL algorithm library too often, is because although they're really neat, the algorithms, oftentimes the routines are so small that you really don't need to use, you know, you only save yourself like a couple lines of code. Actually, in this case, the sorting, well, writing your own sorting algorithm is expensive, so a sort algorithm is like very good, especially like a super optimized kind of like general use sorting algorithm. However, for other things, usually just have like a small loop, and it's kind of like, well, do I really need, like here, this is actually kind of a good example because what I had before was something that looked like this. Ret was 0, and you looped over, I think, each word and words, and then you said ret equals standard max of ret, and you know this gibberish. Like I would actually go so far as to say this is probably cleaner, and then return this. Yeah, this might actually be cleaner than using the accumulator function. You could. Can you auto here? That would be kind of funny. And put the lambda right here. You could do something like that. Maybe do this. I don't know if this is a good idea though. I don't know if this is good to do it this way. You could try it. Yeah, it feels like I'm splitting hairs at this point. Oh. Binary operation. Does it have to be const? Can you do const auto? I don't know if that constant. Of course, we don't want cosant. That's not quite what we want. Incompatible type void. Oh. Oh no, we were fine. We just wanted to do a return. Maybe auto A was fine. It's definitely interesting. It's definitely interesting. Oh, look at that. Does it work? Ah. Huh. Does it matter if we do const auto? I don't think so. I think it'll automatically do that. It's kind of neat. Yeah, I mean, I think this is just like the compiler just decides at one point to go faster, slower. Pretty interesting though. Yeah, like I said, this compared to this and whatever I had before, or returning, calling the accumulator function, it feels like splitting hairs on some level. Definitely at some point it gets a little bit like, I kind of get a little bit uncertain as to what the value is to doing it this way, or because this is like 1, 2, 3, 4, 5, 6, 7 lines, whereas the other one was really like 4 lines, and it's pretty legible. Pretty legible. This is like, or this is kind of less legible, quite frankly. Actually, I mean, you understand what's happening to some degree. However, it's actually kind of decidedly less understandable. It's kind of decidedly less understandable. So. I don't know. I don't think I would want to use accumulate without doing it this way though, because you're defining another variable somewhere, and then like you don't actually need that variable. You could just put it right here if it's small enough. Put the lambda right in there. Max element would be nicer than accumulate there. Interesting. Mask used elsewhere could be part of modified. Nerd happened. Yeah. I feel you. It's really necessary that accumulate to go back to the original word list. Shouldn't all the information have been transferred by the transform so that words is no longer needed? No, because we need the lengths of all the words. Oh, actually, maybe you're right. Let me think about this. No, we kind of do. Well, technically no. You're actually correct about that. Because the pairs, all the information is stored in. So yeah, actually right. No, that's a fair point. That's a good point. Fair enough. We don't need to go over the words. We can do this iterator at the end. This guy. We'd want to save this though. It's external to. The tricky thing though is we need to save. Yeah, that's a fair point. That make it a little bit faster. We need to save where we're looking. We don't want it the fill portion. We want. Actually, we get into kind of some uncomfortable territory because of how we sort at the end. We would need to. Let me do it this way. Let's do it this way. Out or it auto it leaves. So we got these leaves. We're going to fill leaves to the end. We're not going to sort the. We're going to sort the leaves to the external to the leaves. Leaves plus 1, I believe. Yeah, the tree is a vector. Does this still work? Excuse me. Or is it this? Yeah, let's give that a shot, see if that still works. Yes, so why we want to do that is we don't want to sort. So what happened is we wrote these values in, and then after that we filled the rest. When we sorted, everything moved, right? The filled values came to the front, all these other values moved to the side. And the reason we want to save the leaves pointer is we want to use that again down here in our accumulate function, as you described. And we want to go from begin of the tree begin plus external, where those begin, to the leaves. Leaves is just after, right? And then we want to use a P, and we'll say const auto int, which is the mask. Oh no, is it length mask or mask length? Length mask length. I think it's, what do we say? Mask length. Yeah, so mask length is going to be P. And you're right, we only need to use not S anymore. And now we can use mask times query of the mask. M. And length, I'm sorry, that should be the length. What was it before? Size, yeah, the size of the length. Yeah, good call, man. Good call, I like that. I like that a lot. Let's see if this works. Does this compile? Oh, look at that. Yeah, you're right, you only need to call that mask function once. You do not need to do all that work. You need to do all that work. And you said min element would be better? I don't know if you could use min element for this one though. Custom comparator comparing on dot size. You're selecting the max. The additional nodes are all length minus 1, so will not be the longest word either way. You're selecting the maximum. The additional nodes are all length minus 1, so will not be the longest word either way. A little confused by what you're describing there. However, that auto S will accumulate, copy the string every time. Oh, it will. Okay. I didn't know that. I didn't know that. You're right, doesn't need to go to the original word list. And it doesn't even need all of the words either. Or it doesn't even need to go through all of the, well, yeah, actually, no, yeah, I can go through the tree, right. I like to use the standard algorithms even if they make the code longer. A for loop is versatile, it can be anything. When trying to understand code, you will always need to read and understand it. Yeah, I agree, right, it's semantic optimization, not optimization, but I guess how compact or semantic compacting, no, it's not that, it's, I guess we'll just say how easy it is to understand semantically is very important with code. there's a certain degree of like, if you can imbue more meaning into the code, it's easier to understand semantically. Yeah, something like that. Something like that. Which is super important, right? When you're working on code professionally, being able to understand the code is so much more important than so many other things. Being able to show it to other people so they can review it quickly, looking back on it again and trying to understand what you were doing at the time quickly, when you have to add things or fix things, update things. I mean, basically the persistence of your code, the manageability of your code is like super, super important. It's probably more important than a lot of other things. A lot of things, I'll say. Actually, the standard max element would be nicer than standard accumulate there. Yeah, let me take a look at that. Let me see if I can do that. Custom comparator, comparing on size. Selecting the max, additional nodes are all. I don't think I understand what you're referring to there. Unless I'm mistaken, the length field of padding nodes is set to -1. It is true. So as long as one legit node is in the set, its length will be chosen over one of the padding nodes. Context is that the sorting makes handling the padding nodes harder on the max. Yes, at the time it's true. The sorting was making it harder, except I just modified the sort so that we don't sort the padding. The padding, actually, the only reason why we even have the padding in the first place is so that the segment tree is a complete tree, and that way we technically don't even need. The reason we add the padding to the segment tree is so that way we don't accidentally try to grab basically the garbage that would be in the completed tree. We want to make sure that if our algorithm, for whatever reason, happens to try to grab one of those dummy nodes at the bottom of the tree, we want it to just ignore it. And the sorting, originally I did include the dummy nodes, which, right, making it -1 length is actually useful. However, it's not necessary at all, right? Because what this algorithm is going to do is it's going to search the left subtree and the right subtree for any value that works, and can very quickly determine. It's logarithmic no matter what you do, no matter where the nodes are, if they're all on the left side or all on the right side. Although you do want to keep them in the same kind of a block, we'll say, the leaf nodes, so that way the algorithm you get the correct logarithmic runtime. Yeah, it just needs to be in a single block, that's all. Because you could end up in a situation where the left and the right subtrees are both possibilities, and you lose the value of it being segmented in a segment tree if it's not a contiguous block of values, because then you'd end up just visiting potentially half the nodes or a fourth of the nodes, which is O of n over 4 rather than logarithmic. The reason segment trees are logarithmic in the searches is because the edges of the segments, because it's contiguous, you can always assume that the internal calls. So you can basically, the proof is that there's always going to be 4 internal calls per level. The 4 internal calls per level. The 2 outer calls are going to give you 2 more calls. However, the 2 inner calls, because it's a contiguous block, they're always going to stop right there and process, either determining that you don't need to look there or you should look there. In this approach, we're using the segment tree a little bit differently. We're actually stopping immediately on the right subtree. However, we are making a left and right call each time. And yeah, it's a little bit unusual, I think. I don't know, it's a little different. It's not like, I don't think it's like how you would normally use a segment tree the way that we're using it. It's kind of a slightly different than how we normally do, I think. Something like this. But we want to keep it contiguous. I know that much. That much we definitely want to keep it contiguous. Anyway, so max element. Let me think about how we can do that. Well, let's look at what max element does. The problem with max element is I think you need an iterator and a comparator. Oh, I see. Okay. I should say Interesting. There will always be a solution, right? Right. Yeah, the query will return 0. Yeah, that'll return 0. Yeah, that's fine. Okay, that's good. No, I agree. So let's do that. Yeah, the comparator. I agree with you. Let's do max element. There's always going to be something in there, at least a 0. So it's the same values we're iterating over, except we don't need a 0 anymore. And we can just do P. Oh no, we do P1 and P2. P1 and P2. And we say, now I actually think this will be less efficient. And I think this is going to be less efficient, and it's also going to give us, we actually need to be careful here. We need to return the I actually need to call this function too. I don't agree. I don't think this will give us what we want. Well, no. I don't know. Let's see. Hold on. What does this do? No, man. I don't think so. This is going to return. No. This doesn't do what we want. Okay, hold on. No, I think accumulator is better. Although I appreciate your suggestion, though. Okay, I'll show you why I think accumulate's better. The reason is we have P1 and P2, and we say why aren't these doing what I want them to do? I'll explain in a second, in a moment. P1, P2, M1, length 1, P1, M2, length 2, P2, turn length 1 times query of 1 M1 query is less than int was say area 1 or result 1. I think this is a lot messier, in my opinion. There you go. Okay. Now we accumulate, we get this turn vector, and now we have to convert this again. Does that compile? Okay. Unless I have the wrong idea. Oh. Max element, min element, true max element. Anyway. Forward it first, last comparator, right? Compare. These are the no max element. Oh, come on, really? Oh. That's what's wrong. I forgot about that. Alright, there we go. Still get the right answer. However, a bit slower, and the reason is this is a lot of work to do. A lot of extra work. Select the max, as long as one legit node. Yeah, most code is read more often than written. Yeah, I agree with you on that. Right, definitely. You're right, we don't want the query in there. I agree. Yeah, I think it's a little too much. It's interesting. I mean, I appreciate that, but it doesn't quite give us what we're after. Have to do it all over again. Incidentally, the parentheses for the function call are hidden behind your camera overlay. Oh no! Oh, I'm sorry. Oh no, wait. Oh, I didn't mean to do that. Oh, I see. I see that would... Oh. Wait, let me see. Oh, you couldn't see the function call here. Oh, I see. That's probably why you were thinking, oh, we could use the max element. Yeah, this function call definitely puts a damper. Right, that might be why you're thinking max element. That's something about life too. Like, there's this like crazy thing that happens with humans, where they don't have enough information, or they have more information than someone else does, or they don't realize someone else doesn't have all the information, something like that, and you make judgments and assumptions, and it gets pretty crazy. It gets like really crazy. Like why I'm thinking about that or talking about that is I've come to think about this idea about evil being evil in many ways is the temptation, indulging in the temptation to take revenge. Whether or not something is either to take justice into your own hands, whether or not you should or shouldn't, whether or not justice should or should not be served, deciding for yourself in your own judgment whether or not you should deciding your own judgment that you should take justice into your own hands. I think evil is the temptation to do that in many ways, in many times, and comes out that way, and acting on that temptation. The temptation itself is evil. However, obviously acting on it, indulging in the temptation is oftentimes the sort of epitome of evil. And the example I think of is Batman, right? If you recall Bane, the story with Bane in Batman, where those characters wanted to blow up the city. They wanted to nuke the city. And you think for a moment, well, those guys are clearly evil, right? Like they're the bad guys. They're trying to blow up the city. But if I'm not mistaken, I could be wrong, but if I remember, the reason they're trying to blow up the city is because it's so lost and far gone and so evil. In other words, the city itself is so incredibly evil that destroying it would be destroying evil. So the bad guys are trying to nuke the city because the city is evil. They're trying to be the good guys, if you could imagine, right? Now that circles back. However, if you recall in the Bible, Sodom and Gomorrah were such cities, not just like Gotham, and God destroyed the cities. But what's the difference, right? If God can destroy Gotham, but these people can't. These people are the evil ones for doing it. The reason is that God is in control. God's the one who's set to do it. God has the right to destroy the city. You don't have the right to destroy the city, which is a bit of a conundrum. But the thing that's interesting about it is information, right? It's sort of like the people who look like the evil ones actually think they're doing the right thing because of the information that they're looking at and the information we have about them, right? And the perception, right? Who knows what about each other or understands each other. It all takes different perspectives. So it's pretty wild. It's pretty wild stuff. But yeah, nuking cities is basically God did it. So it's one of those things where, and he didn't, when he destroyed the earth, however many years ago, right, with Noah's Ark, he thought to himself, humans are evil, I'm going to kill all of them, and rightfully so. And he didn't say afterwards that I'm going to fix everyone's hearts and make them wonderful and nice and kind and just a joy to be around. He said, I just won't do it again. Meaning, basically, if we got what we deserved, the whole earth would be destroyed, because that's how evil we are collectively. That's how evil humanity is. It should be, rightfully so, should be destroyed. All things taken into consideration. It should all be destroyed. However, God promised not to do that. And so here we are, contemplating if and when do we start nuking cities. And you got to remind yourself, oh, God will take care of that. You don't need to nuke anything. God will take care of that. I realize it's a bit of a tangent, and you might be wondering how I got into all that, but it seemed related to information. It's because you couldn't see that this query was being called, and there's this kind of temptation, like that's one of the ways that things can get really funky if you make assumptions about the information that other people have. Because I might judge you on that and say, oh, why would he think it was a good idea to use the min-max element? And the reason is you didn't see that there was an extra piece in there. And so I might judge you thinking that you had some other reason to think that was better. But obviously it was just a lack of information. But here I am judging you anyway, right? That's the temptation. The judgment. One of the temptations, judging other people. Because you never know. I mean, you really don't know what's going on most of the time. You really want to be less judgmental if you can help it. If you can help it for that reason. Whew. Talking about hidden complexity, right? Yeah. Hidden even from your view. You couldn't even see it. Most people are the good guys in their own story. It's true. It's true. Yes, sir. That's the problem, actually. That's the problem. That's the Christian dilemma. Is that you ask somebody, do you think you're a good person? They'll say, yeah, of course. Of course. Of course I'm a good person. I'm the best person out there. I love me. I'm always right. I never make mistakes. I never have incomplete information. I never make judgments that are maybe a little off, maybe a little bit. Never do things that I regret. No, I'm perfect. I'm a good guy. I'm a good guy, right? In fact, I'm offended you even ask. Ask me if I'm good. I'm perfect. How could you even question whether or not I'm one of the good guys? Yeah, that's actually like the typical response, really. It's terrible too, because I'm so bad with people. Like I don't recognize that in other people, that they all think they're perfect. Like they all think they're great. Like that's and I get so upset and I get so frustrated, I get so angry, and it's a sin because it's like, well, look, like what people are like they're like you. They think that they're as good as you think you're good, and it's shameful. But one of those consequences is like if you try to tell them they're wrong, they're gonna act like they're perfect. They're gonna act like I don't need to hear you tell me what you think. I don't need to hear your opinion. And it's terrible for me because I knowing that I still try to tell people like you're doing it wrong. Here's how you're doing it wrong, and they're like, get away from me. I don't want to know. Obviously, I'm not talking about in context of programming, where actually constructive criticism can be extremely valuable. Well, really in all aspects of life, if you can take criticism, it's extremely valuable. But or it can be. I guess it kind of depends. But I have this I guess bad habit of dishing out criticism where it's probably needed. It's probably worthwhile. However, I don't take that factor into account that like this person doesn't want your constructive criticism. Like your criticism could be anything. They don't want it. Like, you can help them save $1 million. They don't want it. Chances are. And being upset that they don't want to hear it is like, why would you think they want to hear it? I mean, literally to the point of I've had someone tell me flat out, I don't care about your opinion. It's like, I mean, it hurt to hear that, but it was like, what did I expect? Why did I think? Sorry, I'm talking about something totally off now. I'm kind of going on a bit of a monologue of things that they're abstract enough. I mean, you can understand them even though they're abstract, but they're abstractions now about things that have happened in my life somewhat recently. They've been on my mind. Now we need to figure out how to do it ourselves. Destroy the city. No. See that? I don't know if that was what you're talking about, just blowing up cities. No, that's we already know how to do that. I mean, that's literally one nuke and kaboom, that's city's gone. Which is scary. That kind of makes me uncomfortable because basically I'm at a point where I feel like I probably could, if I wanted to, put nukes in cities that I felt, I guess, needed to have them, something like that. Like that's kind of where this is coming from, is because I've been looking at the world and I'm like, man, this is like, I've been doing too much of this, quite frankly. But it's like, yeah, like the conclusion that like the world should be destroyed. It's like that actually is the correct conclusion. It's correct. It's the correct conclusion. It's like, yeah, people are really, really evil. Like it's just they're like just that's what they deserve. Like that's what it is. And it's like, well, God came to the same conclusion. Like he did it. He actually did it. Like he didn't just conclude it. He did it. He flooded everything. And it's like, oh, well, huh. Oh. Yeah. So what does it mean? It's like, well, you got to live with that, basically. You have to live with that. Yeah, so it was on my mind, but that's the other thing. The other conclusion is kind of crazy, as you said, is like we got to do it ourselves. It's like, well, actually, we have not only do we, I would say like I personally could blow up a city. I think that's a possibility. I think that's within the realm of possibility. I don't know, like I don't know how long it would take. I don't know if I could actually pull it off. In theory, I think it can be done. In practice, who knows? But it really doesn't take that much. You just need the right amount of fuel, thermonuclear fuel. You need the right construction, which obviously you could find, the documents to construct. The physics is like, it's not, as I understand, the physics is not that complicated. Like it's not, it's kind of well known what to do if you want to cause basically nuclear destruction. Like you can do that. It might be kind of expensive, but I think if you just give it enough time, putting all the pieces together, probably is not as expensive as you think. Excuse me. Yeah. By the way, the reason why I've been learned about all this is not because I want to blow up cities, but because I was interested in I was interested in actually nuclear power, nuclear fuel for a long time. I mean, a lot of my life, I was like, oh, if you can get a nuclear reactor going, like you could really save a lot of energy. And I was under this impression, like, our culture could use a lot more energy. Like, it just could. Like, there's just a lot you could do with it if you have like really inexpensive energy. Gas prices can go way down, and then the cost to move things goes way down. And then if you can build robots, then making robots do stuff as costs go down, and like you could just really drive down costs. It's extremely economical if you just have like a lot of inexpensive power. So I was like, all right, well, nuclear reactors would be good. And then I learned that nuclear accelerators can be used to actually treat cancer in some cases, in some ways. Which I was like, oh, well, that would be amazing. Like, we could treat cancer, we could bring down, get near utopian energy costs. Like, we got it made. Like, this is great. Like, we should do this. And then I looked at the world, and I was like, oh, I should take all that information and just go right to bombs. Forget all those things, because basically that's the conclusion I came to, is that like, all these wonderful things, these supposed wonderful technologies, which theoretically are possible, they pale. The value they would bring to the world is not even close to the value to how much is being destroyed. That's what I realized, is I was like, actually, like, this is useless. These technologies, like curing cancer, having utopian energy costs, like all of that is totally useless, because basically we would already live in a utopian society if people weren't just utterly reprehensibly evil all the time. Like, that's basically the conclusion I came to. I was like, there's actually no reason to build any of this stuff, because all the problems that they would solve, people can already solve them. Like, these aren't intractable problems. Like, there's no reason to do any of that. Like, the whole problem is just people. Like, people in the first place. Like, your energy costs would already be utopian level. You probably wouldn't even get cancer for the most part. Like, you'd live for 200 years probably. Like, if there were so many things that people just weren't doing that was evil. Maybe not 200 years, but a long time. If you never had to worry about getting murdered or getting heart disease because of the garbage that everyone's being fed, and all the propaganda to live a certain way, and not telling people all about the different health risks of all these different things. And like, there's just like this absolute flood of evil in the world that's like, if you just stop that, you wouldn't even need all this technology. Like, all this stuff is useless. Like, it's meaningless. So you don't even need it. That's then it becomes like, well, then what you got to do is get rid of the evil, right? That's what you got to do. It's like, well, but then how do you get rid of the evil? Well, you take all that wonderful technology, and you instead of pursuing that, you make nuclear bombs and you blow up the evil. That's what you got to do. This is, by the way, people talk about superhuman AI. It's like, no. I'll tell you exactly what that's going to do. There's no what do you call that? There's no question here. There's no how do you express it? There's no like wondering what the AI is going to do. It's like, no, I figured it out already. It's going to come to the exact same conclusion I came to. It's how it's going to do it. It's going to go 1, 2, 3, kill everybody. That's what it's going to do. Because everyone's evil, and it's like, well, if evil people need to go, everybody's got to go. Done. Done. Superhuman AI figured it out. Done. Yeah, it's pretty wild. It's pretty wild. But that's where my mind has been. So thank you for listening to me rant about that whole tirade. It's okay, I'm a cyclist. I'm used to being judged. I can't do right anyway. Cyclist? You mean like a biker? I have to like record that whole monologue and put that somewhere on the internet where people can appreciate it. That's been like years in the making. That whole rant. It's like went through a lot of different things. I literally studied nuclear technology. Not extensively, but enough to get the point. Let's see, a biker. Yeah, a biker. Oh, okay, fair enough. Used to be judged, can't do right anyway. Yeah. I don't. I guess I don't know enough about cycling to just really get it, but I'll take your word for it. I'll take your word for it. Let's see. You wouldn't even need to tear down the ceiling explosion. Just with the mishaps with the demon core, the radiation alone from assembling a critical mass to the city center suffices. The demon core? I don't know. I guess I have to look at that. I saw a YouTube video about that. I don't know. I kept skipping it because I was like, actually, I'm jealous of the guy who put the video together, and I'm like, I'm not gonna watch this guy's video. He's got enough attention. I don't need to. I need to give him more. But now that you mention, I'll probably go check out this video. The radiation alone from assembling a critical mass in the city center suffices. Wow. So you don't even need the explosion. You just. Wow. Wow. Who knows what Super AI would do? There's one singularity in every possible Super AI decision space, and you're not gonna like it. There you go. Basically, that's pretty much it. That's pretty much what I'm telling you. That's what I'm saying. It's just there's one thing that they're always gonna come to the same conclusion, and it's not a good one. Not a good one. Yeah, biker. Car drivers don't take kindly to our kind. Yeah, fair enough. I guess that makes sense. Yeah, I agree. I agree with you. I agree with that conclusion, knowing myself when I'm driving around cyclists, because like I don't want to hit them, so I'm like very uncomfortable when they're nearby. And I imagine other people do want to hit them. There might be some times I might want to, but let's say keep that to myself. No, it's no, most of the time I'm just trying not to hit the cyclists. Yeah, but I have been in situations where I'm like, wow, can these people get off the road? Where, because I live in New York City, or let's say I lived in not Flushing, Bayside, Queens, New York. I think it's Queens, Bayside, and I drove a little bit through, around and through the city. I think I want to say like in Manhattan, like these cyclists in Manhattan, or not even cyclists, just plain old like just pedestrians in Manhattan, right? When you're driving around, like there's just so many of them that you're like, hey, can we just get these people out of my way? Excuse me. It was not as bad as I thought it would be, but it's definitely like you have to be pretty assertive. Otherwise, you're just like stuck waiting for people to move. I'm saying it not necessarily to literally obliterate the building of the city to make it an unlivable wasteland of buildings. Yeah, I understand. Yeah, I see what you're saying. It's yeah, you just need to start creating radiation. And if you have enough radiation, that's it. Done. Whole thing becomes irradiated, and if you even walk close, your DNA just starts transforming into cancer, pretty much. Or not just cancer, but yeah, basically cancer. I mean, it actually probably just starts like falling apart, but your cells and whatnot. But the ones that don't just get destroyed would be basically effectively cancer cells. So yeah. It really doesn't require much. Actually, what's concerning is Wi-Fi boxes, 5G, and even 2.5G, whatever it is, 2.4G. The predecessor to 5G. Basically, this is radiation out of these boxes, because radio waves and radiation, electromagnetic radiation, are effectively the same thing, and it's just how much energy is in each, I guess, photon, we'll say. I don't know. It's a little confusing because electromagnetic waves and light are basically the same thing, which are photons. However, radio waves are also technically part of the same spectrum. So radio waves are X-rays become gamma rays. So